Okay, you need to explain that. Inhomogeneity is in the what field?
In the density field. So
density field. So explain that.
So if something's homogeneous, if you have a block that is homogeneous, there's no gradients within it. It's just a uniform thing of whatever. If you have some luncheon meat, you pick your big pink slab is going to be pretty uniform throughout this whole pink block of
luncheon meat
meats.
As a metaphor. Never heard that before, but okay, let's go with that. So luncheon meat is a homogeneous lump of pink
stuff. Of pink
stuff, meat of various animals.
So that's an example of something that's homogeneous. It's just a uniform medium with no gradients in it, which means an inhomogeneous medium is something that there is variation now.
Yes, got you. Yeah.
Okay, so if you take pork now, not luncheon meat, there'll be
an actual piece of pig. Yeah,
an actual piece of meat. There'll be striations from the muscles and all that kind of stuff. So
it's a really good metaphor, Thomas. I'm impressed.
Yeah.
Hello, welcome to Matter Over Mind. My name is Stephen. I'm an organisational psychologist. Thomas.
Hello, and I'm Thomas, the experimental physicist from the University of Oxford. And today we're going to be talking about the cosmic dark ages. So this was a period in the cosmic history where there was no new light emitted from anything for almost 1 billion years, which is pretty crazy to think. For about 1 billion years, nothing was giving off light. It was complete darkness.
It's mad, isn't it? I think we just pause for a moment and just consider that 1 billion years of nothing, of darkness. You'll tell us what was going on, but I mean that is just staggering, isn't it?
That's about 8% of the life of the universe, completely dark. Well, but dark is there was just nothing being given off. There was no. If you were in the space, you'd be the only thing giving off light. Crazy.
Amazing.
Yeah.
Okay.
So we're going to talk. Oh, sorry. Yeah, go ahead.
Yeah. I was just going to say. So we're going to assume that we started with a Big Bang. Mm-hmm. That is where physicists think it started, and we're not going to address the question of whether the Big Bang is part of something else, or whether it's the beginning of the whole universe. We're not going to address all that. We're just going to say we're going to start from this point where there's a Big Bang, and we'll address the other questions on that another time, because it is a question we've been asked. Mm-hmm. So we'll get into that another time. But right now we're just interested. Big Bang happens, heck of a lot of darkness, billion years. So what's happening in that period then? So let's kind of start from the Big Bang and then move on.
Okay, so as you said, assuming the Big Bang was just an infinitesimal point that just began the universe. Infinitesimal point, it starts expanding. So initially, you had what's called a quark-lepton plasma. So everything was so dense and hot and energetic that the constituent parts that make up the particles, like protons and neutrons and atoms and everything else, it was too hot for them to even form. So if you remember back from the Standard Model episode from a few weeks ago, leptons are fundamental. So these are your electrons, your muons, and so on. And then your quarks, which are also fundamental, which, the collection of quarks make up your protons and your neutrons and so on. So this is a period in the cosmic history, and that lasted up until 10 to the minus 6 seconds after the Big Bang predicted. So that's 1/1,000,000th of a second after the Big Bang. Everything was really hot and dense, such that you just had a soup of quarks and leptons in your plasma. So after this 1/1,000,000th of a second, everything cooled down. So as you expand, this is a thermal property. Pressure, volume, and temperature are sort of proportional to each other in some way. So if you keep your pressure fixed and your volume increases, your temperature will decrease. So that's basically what's happened. Your volume is expanding, the materials are the same, so the temperature has to decrease.
Okay, so just a quick question: how old is the universe, Thomas?
So the universe is between 13 and 14 billion years old.
Okay,
Those are the current predictions. It's like 13.6 or something. This is actually a bit of a contentious topic. There's something called the Hubble tension. So the predicted age of the universe kind of bifurcates, and there's two predictions that are several standard deviations away from each other. But that's another episode, perhaps. But about 13 to 14 billion years.
Okay, so that's and in the Big Bang series, the comedy series on TV, it was 13 million years ago. The universe was in a hot, dense state, and that's pretty scientifically accurate, isn't it? Really?
Yeah, it was in fact quite a hot, dense state. Yeah. Yeah, and even the word there, state, because obviously a plasma is the fourth state of matter. You've got solid, liquid, gas, and then plasma. So it's a good little tune.
Yeah, good little ditty, and you actually learn something from that straight away at the beginning of the series. In fact, that's probably the only thing that you learn on that that comedy series. Okay, so we've got 13 and a half to 14 billion years ago. The universe pops into existence through the Big Bang, and it's like incredibly hot, incredibly dense.
Mm-hmm.
It's a kind of soup of leptons and quarks, and it's completely dark for a billion years. Then what happens?
Well, so before we get to the dark for a billion years, there's a few more points on our timeline to hit.
Okay.
So once 1/1,000,000th of a second goes by,
1/1,000,000th of a second.
Yeah, so that's up until then. It was all just quarks and leptons. So a really short span of time, really.
I'm going to ask you in a minute how we know this stuff, but we can come back to that. So you're telling me that you know what happened in the universe in the first billionth of a second.
Millionth of a second, allegedly.
Millions and millions. Okay, yeah, good.
Yeah. Okay.
Right. Sorry. Carry on.
So we expand past this point, and then everything becomes less energetic. So if you cool down, you have less energy, so everything becomes less energetic. The quarks kind of globule together, and you get protons forming. So at this point, so at this point, everything is still opaque. So optically thick, no light can kind of leave this bubble of stuff. And this is because if you recall back to episode 1 of season 1, when I discussed what light is, it's electromagnetic radiation. And I've just said it's cooled down enough for the quarks to form into protons, and some leptons are kicking about. So we have electrical charges in this plasma. Electrical charges can interact with the electric field. Therefore, they can scatter light in a process called Thomson scattering. So basically, the light is kind of just bouncing off of all the charge carriers, and it's kind of being held in this ball of plasma. So it's all opaque up to this point. So a lot of observational techniques don't work beyond this point. I guess can't probe into this point. So it expands some more, and then you get something called recombination, the epoch of recombination. This is a bit of a funny name because recombination, I guess, implies there was an initial combination, but there wasn't.
Yes.
It's just, but it is what it is. So recombination, what this means now is, again, it's continuing to expand the universe, and it's continuing to cool down. And now it's cool. The electrons that are buzzing around in this plasma have lost enough energy such that they can be attracted to the protons, which are two negative charges electrons, positive charge protons. So then they can sort of become bound to them. They can fall in their potential well. And if you have a proton with a bound electron, well, that's just a hydrogen atom. So you've cooled down enough, recombined. So now you've got a bunch of hydrogen kicking about the place.
Okay, so this is the epoch of recombination. Is that right?
Yes, that's right. Yeah.
I love that. That there should be either a band called the epoch of recombination, or a movie or a book. I love that phrase. How long is the epoch?
So this recombination kind of finishes around 380 or so thousand years after the Big Bang. So lasts
Okay.
about 380,000 years. So it's quite a long.
Okay.
Well, I say
Quite a long time then. Okay.
Relative to what's happened in the universe, this is a long
Yeah.
period of time.
So that's getting on for 500 million years, isn't it?
Hello, Editing Stephen here. So I'm on holiday at the moment and I've got up early. Kids are in bed, Sarah's in bed, so it's just me in my dinosaur pyjamas doing a bit of editing for the podcast. And just noticed that I said 500 million years in my statement just now, and it should be 500,000 years. It kind of messes up the whole timings for the universe. So wanted to be scientifically accurate. So there you go. So this is Stephen editing. I hope you don't get to see Editing Stephen again during this podcast. If you do, it means I've made another mistake. So that's it for me. Back to the podcast.
Because that isn't that as far back as we can sort of see. We can with our optical telescopes. You're laughing. Am I getting it badly wrong?
No, you've got it spot on.
Okay,
exactly. So at this point of recombination, so all the electrons are sort of falling into the potential well of the protons. And then in doing so, they don't initially fall into the ground state. That's relatively unlikely, probabilistically speaking. So what will happen is you've got your proton, and electron will zoom past, get trapped in its potential well, kind of be in a high energy state, and then when it drops down from its high energy state, because it'll eventually try and sort of work its way down to the ground state, it will emit photons. It'll emit photons that will de-excite it, and then eventually it'll fall to the ground state. So eventually, once enough of this happens, then light can what's called decouple. The photons can decouple. So basically, if I have a hydrogen, a proton with an electron, which is a hydrogen, if that drops down an energy state, that will emit a photon. But if I have a close enough other hydrogen atom, then that electron may absorb that. So there's a bunch. All the photons are coupled to the rest of the plasma. But once everything de-excites enough, the photons decouple and they begin streaming through. So now the light can escape this kind of hot bubble that was trapping it before. And this streaming, that's that light. I guess the first light that can escape the hot bubble, that's the CMB. That's the cosmic microwave background.
Oh, wow.
Yeah, so exactly right. That's the reason we can see back until about 500 million years is that is the first light that was able to escape the plasma bubble.
That's amazing. So we're not going to get any further back, are we?
No, not with optical methods.
No, I suppose there might be other ways of doing it, but that's okay. That's really interesting. So that's the background microwave. Sorry, what did you call it?
The cosmic microwave background.
Cosmic microwave background. Yeah.
Yeah.
Wow. Okay. We're racing through this.
We are speeding through the universe. So what's interesting here is, as I said, kind of to allow this light to escape. Also, some keen listeners might be noting, hold on a second, the hydrogen transitions aren't microwaves. So how did that happen? We'll get onto redshift in a second, but that's why it's microwaves, even though for example, Lyman transitions aren't in fact microwave in frequency.
Okay.
But anyway.
So we've just got a universe that's only got hydrogen in it at the moment. Is that basically it?
Pretty much, yeah. There's some helium and some trace lithium, but mostly it's just hydrogen.
Okay.
So when the hydrogen, or when the electrons within the hydrogen de-excited enough such that photons can stream, everything's kind of chilling out. If you have a proton with an electron, that's just neutral hydrogen. When everything de-excites enough and everything's neutral, nothing's interacting. Everything's in an energetically favorable state, so there's no reason for it to do much. And because of that, there's no need to emit light. So this was the beginning of the cosmic dark ages, because everything combined together. It kind of calmed down from its excited state. The photons left on their merry way, and they're no longer being absorbed by the surrounding plasma. So everything's just in equilibrium and not interacting. So
okay, so let me just, that's new to me. That, so what you're saying is there was a Big Bang at which, well, this epoch where there's reconstruction is happening. That is that there is light there of a sort within this kind of bubble of expansion. And then there's this period of darkness. Is that right? So we get light and then darkness.
yeah, so I suppose I should caveat the Dark Ages. There's no new light. So obviously the CMB, the cosmic microwave background, still exists. It's the initial light that was giving off is still there, but obviously that will deplete over time as your universe expands. Your light becomes more diffuse. It's spread over. If you imagine a drawing on a balloon, the bigger you blow the balloon, the more spread out the image is. Or in light's case, you have what's called the inverse square law. So if I'm 2 meters away from a light source, it'll be 4 times dimmer. If I'm 10 meters away from a light source, it'll be 100 times dimmer. So it's 1 over distance squared for light. So as the universe expands, this CMB becomes dimmer and dimmer. But yeah, because everything is now neutral hydrogen on the most part, and some dark matter is also kicking about. But dark matter is dark, so that doesn't really matter.
We can ignore that for the time.
Yeah, we can ignore that.
Okay.
But yeah, everything's neutral, so it's not giving off, it's not radiating anything. So there's no new light for a long time. So kind of crazy.
Yeah.
Okay. So how are we no longer in this epoch? How did that happen?
That's the question I'm going to ask. Thomas, how come we are not still in that period? Well, what happened? It was all stable. There was nothing happening. No lights. What happened? How did it become unstable?
Yeah, good question. So
thank you.
So as I mentioned before, there are some trace amounts of lithium and helium kicking about. And if you remember your periodic table, those are heavier than hydrogen. So what that basically means is there's some inhomogeneities in the density field. So you
need to explain that. Inhomogeneities in the what field?
In the density field. So
density field. So explain that.
So if something's homogeneous, if you have a block that is homogeneous, there's no gradients within it. It's just a uniform thing of whatever. If you have some luncheon meat, your big pink slab is going to be pretty uniform throughout this whole pink block of
luncheon meat as a metaphor. Never heard that before, but okay, let's go with that. So luncheon meat is a homogeneous lump of pink
stuff.
Meat of various animals.
So that's an example of something that's homogeneous. It's just a uniform medium with no gradients in it, which means an inhomogeneous medium is something that there is variation now.
Yes, got you. Yeah.
Okay, so if you take pork now, not luncheon meat, there'll be
an actual piece of pig. Yeah,
an actual piece of meat. There'll be striations from the muscles and all that kind of stuff.
It's a really good metaphor, Thomas. I'm impressed.
So that's good. It's all physics, isn't it? So basically, if everything was neutral hydrogen, you'd have a homogeneous universe, right? Everything would weigh the same, have the same charge, and just it will be the uniform, and nothing's going to happen. But if you have lithium and helium dotted about, so helium is twice the mass of your hydrogen. Lithium, I think lithium is 6 or something in the periodic table. I can't remember, but it's a bit heavier as well. So what that means is you have mostly the same, with a few bits of heavy dotted, sprinkled around. So these little heavy points, and also there's a sort of dark matter halos that are sort of kicking about, but we won't talk too much about that because the analogy works kind of without it. But these heavier little sprinklings, they kind of act as nucleation sites. They act as seeds to sort of start a gravitational snowball effect, I guess, right? If you have something heavy or relatively heavier than something else, it's going to attract some stuff. Okay, it attracts something. Suppose the closest hydrogen next to it is going to collapse. It's going to attract it in. Well, now it's even heavier. Okay, so more stuff's going to come in. Oh, now it's even heavier, and more and more and more. So basically, you get these sort of little pockets forming where matter is just accumulating. So this process kind of seeds the really early stars. They're called population 3 stars or low metallicity stars. Low metallicity because they're comprised completely of hydrogen and helium and lithium. There's no heavier elements than the first couple on the periodic table at the moment. Okay,
so let's just pause for a minute. So there's been like 1 billion years of darkness, and then imagine we're observing the universe as a kind of, from the outside. You start to see little pinpricks of light as stars start to pop into existence. These very early stars that are beginning the process, I suppose.
So initially, I guess that's right. Yeah, you'll get these little sites starting to form, and stars will begin to form. So this starts happening around 600 to 700 million years after the Big Bang. So not quite 1 billion.
Okay.
You start these things forming, and it's predicted to this period of everything kind of reionizing. It's called the epoch of reionization. Starts to happen, and this ends around 1 billion years after the Big Bang. So this process of, by the time all the lights have been switched on fully, that's the end of this sort of period.
Got you. Okay.
So these stars start sort of collapsing in, start forming. Then when these stars they're low-lived, they're sort of low-lived. Short-lived. Long-lived. Short-lived. Because everything's low mass. All the fuel is light comparatively to what we have now, at least. So these things start supernovaing all over the place, and that's spewing light and radiation in all kind of places.
Okay, so let's just talk a little bit about how the stars are forming. So this is I've heard this talked about, so I'm going to have a go at explaining it. So let me know if I got this right. So essentially, if we're talking about hydrogen, mainly hydrogen, all this matter is sort of clumping a little bit, and as it starts to come together, attract other hydrogen atoms, the weight of all of that stuff starts to it makes it hotter, it heats up, and it's that heating that effectively creates a sun. So it's like collapsing hydrogen in on itself, and it's that creates the sun. Is that right, or the star?
Yeah, exactly. Yeah. So if you have enough stuff falling into itself, eventually there's going to come a point where the outward pressure of the stuff is going to basically cave in. So if you imagine you've got a tin can, if you squeeze it, there'll be some give, some outward pressure, but eventually it's going to give and it'll crush. That's kind of what's happening. You're accumulating mass and mass and mass, and eventually the gravitational force will overpower the outward pressure of the material kind of pushing against each other, and then it'll collapse in and then become denser, and then more stuff falls in, and so on and so forth. And then obviously the higher pressure you are, the higher temperature, and it's a bit of a feedback loop. So eventually the stuff in the core becomes so compressed and it becomes so hot that it begins to fuse. And that's then once it starts to fuse, we have fusion, and then it starts eating up the fuel of the star. And then when it runs out of fuel, given some criteria have been met, it will then supernova.
And when we say fuel, we're talking about the hydrogen, basically. It's running on the hydrogen. Yeah.
Yes.
So that's the fuel. It runs out of the fuel. And then, so it's no longer able to essentially burn, fuse. The fusion stops happening because there's no more free hydrogen for it to use. And at that point, it's just mass. And that's when that's when it goes supernova. In other words, it kind of explodes. What's left, it just kind of booms. explodes.
Yeah, exactly. So, I mean, think about it this way, right? So you've got your sphere of hydrogen, and in the core is fusing. So when you're fusing, you're getting one light element and a second light element, and you're smushing them together. Now you have a heavier element. So that keeps happening. Eventually, all your light stuff, all your hydrogen is going to be used. You're going to have some helium and some other stuff left. Okay, well, if it's not hot and dense enough to fuse the heavier elements, well, then it's not going to do anything, right? So eventually these things are going to be kind of kicked out, and you're going to kind of imagine this sort of hollow stuff that was fuel, and now it's kind of thermally pushing outwards, and then that's the heating. And then once it stops being able to burn the fuel, it can have no longer thermal pressure pushing outwards because it's run out of the hot stuff. So then the gravitational pressure is going to collapse it in, and it collapses in and basically booms outwards, and that's what the supernova is. And then
and
so that's happening.
That's the supernova.
Yeah. Like I said, there are some more caveats, but essentially, if you're hot, you have high pressure. So in the case of stars or a lot of astro systems, you have external thermal pressure where the hot stuff's in the middle pushing outwards because it's hot, and you've got gravitational force outwards pushing in. One of them's going to win, and if it's if the thermal stuff cools down, then suddenly the outward force is less, the gravitational force is the same, so it collapses in, and eventually it'll increase the pressure to such a massive extent that then the thermal pressure wins out over gravity, and it just pushes everything outwards.
And that's the explosion. Okay, so we've got these early stars. What did you describe them as? What they're called?
They're called population 3 or low metallicity.
Population 3. I'll use that first one. Population 3, because I don't think I can pronounce that second one. Population 3 stars, and so they pop into existence for a while. They're fairly short-lived, and then you see in the universe, we're looking at it again from this external vantage point, and then you start to see these supernovae going off all over the universe.
Exactly.
That's what we're seeing next.
When supernova happen, it starts basically spewing out these heavier elements that didn't really exist before, and these heavy elements kind of spewing out everywhere, so then sieve the galaxies to start forming. You can accumulate more mass more quickly, and then you get galaxies forming. And then with galaxies, you have quasars, which are basically just really highly emitting galaxies, basically. So all this stuff now is kind of exploding and creating bigger stuff that is then shooting out radiation all over the place. So actually what ends up happening is you get this sort of patchwork of bubbles forming independently. So in between the bubbles, it's still completely dark. Or at least nothing is being emitted. But then you just have these bubbles forming and expanding and kind of overlapping each other. And eventually, when enough of these bubbles are around and they expand big enough, they start overlapping again. You've now sort of switched on the lights. The sort of universe has become saturated with light again. And now reionization has finished, and we have the lights have been turned back on.
Wow. And this is the beginning of the stuff that we're made of, the stuff that planets are made of, the stuff that like gold and other precious metals, all of these things were created in that period where there's these early stars that essentially generate all the materials that we're going to use in the universe. These type 3 suns.
Yeah, isn't that amazing?
It's amazing, isn't it?
Yeah, and it kind of makes sense, right? So when I was learning about this, it was as I was reading through these papers and all this, I was like, yeah, obviously that makes sense.
Yeah,
sure, you're going to get hydrogen first, and how else would you have these heavy iron? How does that happen? Well, it only happens because you have these violent explosions forcing it to happen, but that doesn't happen until you have stars. It's just amazing to think that from just a sea of just uniform hydrogen that's kind of ambiently doing nothing to then just basically just random fluctuations in density throughout your space, really slowly gathering stuff such that eventually you can then be big enough to make something happen. And
there's a kind of philosophical lesson here around sort of the need for difference and the need for things that are essentially putting a spoke in the wheel. The universe was nice and stable. It was all fine, but it's doing nothing. It's doing nothing for nobody until there's some difference, until there's something in it. There's some impurity in the universe that forms these little pockets of stuff that is interacting with each other, and then you get this sort of chaotic scene that starts to create all the materials that we need and we use every day in our lives, and without which we wouldn't exist. So that is fascinating.
Yeah, I mean, yeah, it's really cool to learn. I mean, when we learned about it, actually, I read into this in my master's, and so my cosmology course, part of the assessment criteria was, we've taught you X, Y, Z. Now, read up on a topic we've not taught you. There's a list of things to cover, but basically, we've not taught you this. Go read up on it and then present to your cohort. And this was the topic I chose. And I didn't know anything about it. I just thought reionization, sure, why not? Sounds cool. And yeah, I kind of learned all this stuff. It was really, really interesting. But also what I find interesting, and maybe not for some people, but is how you can see the point at which the light's turned on. If you look at the spectra of the universe. So obviously the cosmic microwave background, the CMB, there's that kind of really famous image, which is like an oval shape and a kind of a green splodgy image. So everyone's kind of seen that. So you can see that. But the way they found, this sort of epoch of Dark Ages and reionization, it was theorized for a while, but it's not until I think it's the 70s where they actually, or maybe the 80s, I'm not too sure, or maybe even more recently than that. It wasn't that long ago in the grand scheme of things that they even found that this was real. So two people kind of have the name associated with this discovery, Gunn and Peterson. They predicted what's called the Gunn-Peterson trough. And essentially what they thought was, well, if everything was hydrogen, and then everything starts, blowing up and spewing out light everywhere, hydrogen comparatively to other elements, at least, has a very simple spectra. So you've probably heard me talk before about the sort of quantum levels in an atom. So you've got the energy level shelves. If you drop down between one shelf, you emit a photon of corresponding energy drop. So if you have hydrogen, there's a very specific line called the Lineman alpha line, or the Lyman alpha line. This is a transition from the second shelf to the bottom shelf, basically. That line has a very specific energy associated with it, which means if hydrogen has that energy associated with it, if you have something in the ground state, it can easily absorb that specific frequency to excite an electron upwards. So what Gunn and Peterson theorized was, if there was this period where everything was completely just saturated with hydrogen, and then light started going off, well, they're going to absorb this specific wavelength. So it's going to be opaque or optically thick to that wavelength, to the Lyman alpha line. So what they predicted was, okay, if you look at the spectrum of the universe, you should only really be able to go back in time far enough before you stop seeing this wavelength of light. So when they go back, the light gets redshifted. So basically, if stuff is traveling away from you, the wavelength stretches, therefore it's more red. If it's traveling towards you, it compresses and it's more blue. So it's just Doppler shift. You'll hear it if a car whizzes past you. It goes, high frequency and then low frequency. So the
I've
same
made
thing.
this joke before. Celine or Sarah, my wife, always sort of teases me about this because it's my little fact that I like to, my little dad facts. Do you know what that is? That's called the Doppler shift. That is, So anyway, I like to have my little facts.
No, it's a good little effect. So if you go back in cosmology, generally they measure time and redshifts. So the greater the redshift, the farther back in time stuff was.
So this is when you say going back in time. Basically, we're saying we look out into the universe and the
Yeah.
further out we see, that effectively is going back in time, and we're looking at that redshift because we are looking back in time.
Yeah, exactly. Imagine you're in the center of a balloon as it's expanding. The stuff on the inner wall of the balloon is, it's the farther out it is, the longer it's been expanding for relative to you, right? Yeah. So, exactly. So you just look back at really old galaxies, basically. And how you can tell this is the same, that specific Lyman transition, is because in the same way, if I put my little fingerprint on a piece of paper or a piece of elastic and stretch it, it's just because it's been stretched, it doesn't mean my thumbprint's changed. It's you could still, if you look at the stretched image, you can in principle unstretch it and be like, oh, that's Thomas's thumbprint. So these signatures are very specific, so you can stretch them and kind of warble them as in whatever way, and you can de-transform them. You can kind of inverse that stretching to be like, oh, this is cool. And hydrogen, exactly. Hydrogen's abundant in a lab. You can very easily test what the transitions look like. Fine. So if you look back at spectra from galaxies and what have you, the farther back in time, from a billion years and older, you would expect to see a dip in this specific line because of how much hydrogen there was in the intergalactic medium. They predicted you'd see this trough. And it was funny when I was reading into this because reading papers before it was observationally proven, there was this other paper basically being like, here's my theory, Gunn and Peterson talking rubbish, there's no evidence whatsoever about this trough. And then I read the actual paper where they're like, look, and there's a picture of it, you can see some spikes, and then you increase the redshift number of a different galaxy, and then suddenly it drops off. So you can see this dip in your frequency band. And then after that point, there was no, obviously you saw it, right? But it was just really interesting that this one paper was like, it's a load of rubbish, there's no proof. And then within a year of this paper, they proved it, and it was like, well, I guess
and that's science at its best, isn't it? That's it's until we have evidence. Hypotheses are welcome, but once you've got the direct evidence, then you have to adjust, don't you, for it? Because that's what it's showing you.
Yeah, exactly. Right. So this was I guess a good way of, if you follow the steps, it logically makes sense. That's kind of the procedure. And then the fact that Gunn and Peterson found this trough in the Lyman series basically says not only the universe was full of hydrogen, but at around redshift 6, which is about 1 billion years ago, that's when we started seeing these lines again. That's
1 billion years. Not a billion years ago.
Sorry. 1 billion years after the Big Bang. It's a non-linear scale, so redshift 6 doesn't sound that long ago. We're on what, redshift like 12 or whatever now, but it's non-linear, so it gets confusing.
Right. Okay. So I asked you before how we know some of this stuff. So you've kind of explained some of that already with your discussion there around the redshift and all of that. How do we? Are we basically extrapolating what happened in the first, billionth, millionth of a second, whatever, just based on, what it could be? I guess nobody's around then. We're never going to observe it. How do we come to those conclusions about what's happening right at the very beginning of the universe?
Yeah, it's a good question. I mean, a lot of it is wrapped up in a lot of heavy theory because, like you said, anything before the cosmic microwave background, any optical test is invalid. You can't, light didn't really exist in a proper way before then, so you can't see anything. I guess what you can do is so one of the things they do is they look at, for example, fluctuations in the cosmic microwave background. Then they think, okay, well, there are these fluctuations and then they can kind of theorize, okay, well, basically, imagining this model of basically a ball expanding, if you contract it in, certain signatures can only really happen if other stuff has happened first. So you can be like, okay, well, basically those three things happened, I don't know, say 3 arrows shot out. Okay, well, there's 3 holes there, so they probably came from about there. And that's the kind of arguments that get made. They're like, okay, we can see this pattern, so let's basically wind the clocks back. Oh, okay, they meet there. Okay, cool. And then this one, oh, they meet there. And interestingly enough, by doing that, it turns out if you kind of do that sort of procedure, this bit meet there, this bit meet there, they don't all meet in the same spot, which is how inflation kind of started to be a thing. They had to realize, oh, maybe it wasn't a sort of a uniform expansion. Maybe it was exponential expansion, because otherwise these things kind of don't really converge in the right way. So that's the kind of.
So you've made your own bed now, Thomas, because you said we weren't going to talk about inflation. And you've mentioned it, so I'm gonna go there, but we don't need to get into it in a big way. But as we've mentioned it, I guess we should explain what it means. What is the theory then that relates to this thing called inflation? Because it's not just the expansion of the universe like one might think. So we're talking about something very specific. So what is inflation when we talk about that in terms of the universe?
You're right. Inflation isn't just the term for the universe inflating. No, the universe is expanding. The inflationary period was a specific point in time. So directly after the Big Bang, there was this period of inflation. So what that means is, instead of, at the moment, we have accelerated expansion. So, there's a set of equations that govern, or that describe rather, how the universe is expanding and how quickly. But if you, so if you have a number line, that's expanding upwards, fine. If you trace it backwards, it doesn't get to the origin. So imagine you've got a straight line because it's accelerating, cool. But it kind of gets to a point and then suddenly it really speeds up. So there's a point a little bit after the Big Bang where it was exponentially, like an exponentiated acceleration compared to now, which is what's called a linear acceleration. Inflation is a very specific period directly after the Big Bang where everything was expanding at an exponential rate before it kind of calmed down and then just started expanding normally. So inflation is a period of time, not.
So it's I find it fascinating and deeply unsatisfying, and I'm very skeptical because it just feels like, so you get the Big Bang, so the universe goes bang, and then all of a sudden there's like massive, it goes whoa, like way out, and then it slows back down again to a normal expansion. So it's like bang bang, and then off you go, forever expanding. And it feels like that's a fiddle factor. As a non-physicist person, it feels like, okay then, you've had to say that because your numbers don't add up. All right.
To some extent, I do agree. Actually, I think, to some extent, I do agree. It feels a little bit. Well, we don't really know what happened, so let's just fiddle around some theories.
We'll call it that. We'll say that. But I mean, all the experts and all the major theories seem to be pointing to it, and from what I understand, the most recent experiments and observations still support the idea of this period of high inflation, this period of inflation soon after the Big Bang. So I guess the evidence is there, but it's kind of weird.
It is strange. It's a weird one, and perhaps we can do an episode in the future. I need to do a bit more reading up on it. But it is interesting. I guess also, back to the balloon analogy, when you're blowing up a balloon, there's a little bit at the start where it's kind of hard to get it going. And then, you blow in, it builds up some pressure, then it zooms up, and then it starts kind of opening normally. So I guess you could maybe think about it that way.
Yeah, that's true. You're very good with your metaphors today, Thomas. I'm very impressed. There's lots of really good ones today.
Yeah, on a roll,
fair enough. Okay. All right. You've kind of answered my question about how do we know? We don't observe it directly. I guess we simulate the Big Bang. So we see in simulations, in models, what it would look like if it did this and if it did that, and see how closely it matches the universe that we see around us. So that's another thing, I guess, that we do. Okay. Anything else? Anything else about the so maybe, unless you've got something else to tell us about that historical period, and you haven't prepared for this, so you can skirt it if you like. But what happens in the future? So we've got this time behind us, and it's a very exciting time with the light switching on and creation of all this stuff, and as far as we know, we know that the universe is speeding up in its expansion.
Yeah.
So what does the future hold then for the universe?
So that's the question, isn't it? The big question. There's sort of three potential outcomes, really. There's the case where we live in a closed, an open, or a static universe, I guess. So either we'll kind of expand and get to some maximum expansion and kind of just stop the outward force, whatever that may be, and then the inwards pressure kind of equilibrate, and then we're stationary. There's a case where we continue to expand indefinitely, or then there's the case where we get to some point and then the outward pressure overcomes the inward pressure, and then we recollapse, and then we crunch up a little bit. So I guess in the event of the crunch, we start zooming back in, everything becomes hotter and more energetic, and then we just turn back into a quark lepton soup again. So I guess that's one. Okay. I guess the case for the continuous expansion, or the static case, at least in my opinion, once we get to those points, everything decays eventually. So all the stars eventually will run out of fuel and supernova, and then the results of those supernova will eventually be used up. Whatever they decide to excite. Everything kind of decays into a ground state. Even protons decay with a long enough, or they're theorized to decay rather, with a long enough time span. So basically, entropy's relentless march will go on. Everything will become in a state of, I guess, maximum entropy, which we'll definitely do an episode on entropy in the future, because there's a lot of interesting thermal physics to talk about. But eventually things will decay. They'll kind of all, de-excite to their ground state, and then everything will just be kind of a cold, hot mess again, I suppose. A cold, dark mess, not hot.
Yes. Yeah. Okay. That's I don't know. That's the one that I think Brian Cox on TV talks about, as the universe gradually sort of everything becomes detached from everything else. Yeah. You end up with just isolated quarks, and eventually there's nothing. It's completely lifeless and cold. And that's really unsettling. I don't like that one at all. I don't like that one. I feel like even if I'm not here, which obviously I won't be, I still want the universe to carry on. You know what I mean?
Yeah, no, it is a little bit sad. But, this would be in so many billions of years.
Oh, yeah, of course. I'm not worried about it, Thomas.
It's going to happen next week. The end is near. It's one of those things where, the more I was learning, and maybe this isn't why I'm a theorist anymore, who knows, but I was learning more about, quantum field theory and particle physics and cosmology, and I was just getting a bit existential. I was thinking, we're all just random oscillations in a field that eventually will just decay away.
It's kind of, everything that has ever happened will just, anyway, let's not dwell on that. It might not be that. So we all sorts of things might happen. So let's not worry about it. Let's imagine that there is some next phase, because of course it could be that we are, if it all goes back into the Big Bang again, either through a crunch or, as Roger Penrose talks about, basically once you get to that state, effectively you're at the beginning of the universe again. So it's almost like it's a kind of cyclical thing. So it could be that maybe this is the first time round, or maybe it's the billionth time round. We just simply don't know.
Exactly. Yeah. Maybe we'll have another dark age and then another re-ionization. Yeah, there we are.
Okay, let's go for that one then. All right, is that it? Have we covered the universe and the history of the universe?
Yeah, pretty much.
Okay, I think we've done that.
A big chunk of it, at least. Yeah.
Okay, so there's a few things to refer back to. We're gonna do an episode on entropy. That's an important one, and inflation. Perhaps at some point we'll get into the weeds on that one as well. So there's quite a few bits still left to discuss. But I've found that really interesting, Thomas. It's a fascinating topic and mind blowing, I would say.
Yes, indeed. Yeah.
Okay.
Thank you.
Well, thank you, Thomas. Thanks for that. And everybody, thanks for listening. Don't forget to like and subscribe and go tell your friends about the podcast. We've kind of hit a bit of a wall in terms of listeners. So we kind of need you to go and create some more, please. So let people know about the podcast. We're a minnow, compared to so many other really big podcasts, but we'd like a few more listeners, so let people know about us. And don't forget, you can join the Facebook page. It's a good one because it's free and it's open. You can join it, and we do put pictures and we have little chats on there, so if you want to interact and ask questions, that's a great place to go. So join us on the Facebook page. Okay, thank you very much.
Thank you. Goodbye.
Bye.